The COVID-19 pandemic has led to a dramatic increase in the use of face masks. For this reason, from the University of Alcalá in Spain, we have conducted a study on the effect on face mask on forensic speaker recognition. Our study is organized in the following four sections: an introduction, where we mention related works and the threat model; the methodology followed, where we explain how the voice recording were obtained, the acoustic features, and the automatic speaker recognition model used; then the results obtained from the model and the intensity analysis; and finally, conclusion and future work are presented.
Let's start with a brief introduction to the subject. Speaker recognition is the task of identifying the speaker behind an acoustic recording. Therefore, forensic speaker recognition involves the identification of a person in any possible speech recording scenario at a crime scene. Recognition systems encounter difficulties with the introduction of some alteration in voice production, which limits the admissibility of recorded voice evidence in court. For example, by the introduction of elements that affect its production, as in the case of face masks. Under difficult forensic conditions, speaker recognition techniques cannot produce reliable speaker comparison results. The use of face masks has increased enormously worldwide due to the COVID-19 pandemic, and there is no denying the barrier masks pose to the act of communication. So, do masks have effect on acoustic voice evaluation? Several studies, both before and after the COVID-19 pandemic, address this question. Previous work has shown that the use of masks results in a significant loss of speech transmission, which varies according to the type of mask used. However, they are not contemporary to the COVID-19 period and do not address the problems encountered in relation to voice matching. The most recent studies suggest that masks alter the intelligibility of speakers by producing variations in relation to the distribution of acoustic power across frequency bands. Furthermore, there are very few related studies, and none of them with Spanish speakers.
In most cases of forensic speaker recognition, a recovered acoustic emission is compared with a control acoustic emission, where an expert must carry out an analysis of both voices to conclude whether the signals correspond to the same person. To make this comparison, professionals of the state security forces and corps work under the premise that the control sample obtained being generated under the same conditions, or with the highest possible degree of reproducibility. However, as a result of the pandemic and the obligatory use of face masks, the conditions for obtaining control samples were slightly altered. The problem is that covering the face induces an alteration of the properties of the acoustic signal and produce an added challenge for the work of experts. Forensic voice analysis has several drawbacks, as voice has a number of factors that generate variability. Covering the face with face masks implies both intrinsic variability, the mask will affect speech production, and extrinsic variability. It will affect speech production and intelligibility, and also absorb the transmitted voice signal. Also, the impact of face masks on speech production doesn't occur to the same degree with all type of face masks, but is dependent of the specification of the individual masks. According to the guidelines of the European Network of Forensic Science Institutes, (EMSI), the presence of circumstances that hinder, modify, or alter evidence during the evaluation stage may limit the admissibility of voice in evidence in court. In this study, we test a automatic speaker recognition model based on support vector machine, with samples recorded under different conditions than those used in the training of the model. Specifically, we test the strength of the classifier against acoustic signals obtained in the presence of two forensically relevant face masks, surgical and FFP2. This has to lead to the following hypothesis. One, the use of face mask has an impact on the automatic speaker recognition model, decreasing the efficiency of forensic speaker identification. And two, the use of FFP2 mask will result in a lower hit ratio in speaker identification.
This section will develop the process followed to reach the results and their subsequent conclusions. The methodology followed can be classified as inductive. The study involved 30 Spanish speakers, 15 female and 15 male. These participants had to read three balanced sentences in three different conditions. The first one wearing a surgical mask, the second wearing an FFP2 mask, and the last not wearing a mask that represent the control samples. In this way, a total of 2070 voice samples were obtained, with no notable interferences and under controlled conditions. The recording environment was the same for all participants. The room noise level was measured to avoid possible interferences in the subsequent analysis of the recordings. The entire speech set was captured with an Olympus LS100 recording device at a constant distance of 30 centimeters from the speakers. Recordings were obtained with a sampling frequency of 44.1 kHz and a resolution of 32 bits. Then the signals were pre-processed with Audacity to homogenize the duration and eliminate the silence. Here we will listen to some examples of the audios that make up the generated database. We have chosen speaker 4 and sentence 1 in all three recorded conditions. How to listen the first one with surgical mask.
La camisa blanca del pastor está fabricada por las chicas más graciosas de Talavera.
The second audio with FFP2 mask.
La camisa blanca del pastor está fabricada por las chicas más graciosas de Talavera.
And the last audio with a no mask.
La camisa blanca del pastor está fabricada por las chicas más graciosas de Talavera.
As we can see in the transcriptions, the sentences don't make much sense, but they are made up of features that make them interesting from the point of view of speaker identification. For example, they have a lot of vowels and a lot of S's, which in Spanish are very individualizing characters. The database generated and the algorithms used is publicly available at GitHub. Table 1 shows all the speakers involved in the study. With each of the three conditions, three sentences were recorded. This generates a total of 9 recordings per speaker. As a previous step to any automatic speaker recognition system, the acoustic features of the voice have to be extracted. For this stage, we use Librosa, a Python library for audio processing. The features that were extracted from the speech signal correspond to spectral ones, because spectrum reflects the anatomical structure of the vocal tract, so different speakers will have different spectrum. In addition, an advantage of spectral methods is that logarithmic scales, which mimic the functional characteristic of the human ear, could be used to improve the recognition ratio. There are different features that can be extracted: Mel spectrogram, Mel frequency cepstral coefficients, chroma, tone, and spectral contrast. However, many of these features are related and can lead to misclassification errors since the feature vector composition is redundant and confusing for the classification system as well as inefficient. Tests were carried out during training to evaluate the most efficient acoustic features for the model. The best results were obtained using only the Mel frequency cepstral coefficients, specifically 50 per audio. They are a set of features extracted from the spectral domain representation of the speech signal that concisely describe the general shape of a spectral envelope, represent the vocal timbre, and one of their main advantages is the isolation of noise, or the removal of irrelevant information from the sound background.
An ASR system acts like a pattern classifier. Each pattern consisting of a set of previously extracted features from the speech signal that allows speaker identification. In this case, the classification is carried out using supervector machines. In order to build a robust model that correctly assigns speaker identities, it is essential to have a properly trained SVM classifier. For training, we have the set of unmasked audios, and a total of 30 classes corresponding to the total numbers of speakers. In the training phase, three different models were used, corresponding to the combination made with two of the unmasked audios set for each sentence, and the remaining sentence were used for testing. In the slide, we can see the best hyperparameters values to train the model. Therefore, recombining the audios of these three sentences allows training the ASR system with the whole set of unmasked audios, obtaining a robust model. After the training phase, accuracy of 100% have been obtained for all the model tested, as we can see in table 2.
In this section, we would like to talk about the results obtained. In general, a decrease in the accuracy of the automatic classification model can be seen when one of the masks is used. When the training and test sentences are pronounced without the use of the mask, the ratio reaches 100% in all test cases, as we can see in Table 3. However, when we introduce sentences with a mask, there is a degradation of the performance of the model, introducing errors in the speaker classification. When we train the model with audios in the presence of one of the masks, things change. The recognition system improved identification ratios, reaching 100% accuracy in all cases, as we can see in Table 4. The method used has been exactly the same conditions, same feature extraction, so this result seems to confirm the first hypothesis, that the use of masks has some effect on the automatic speaker recognition model, decreasing its efficiency. In this slide, we have added an example of a confusion matrix for each of the conditions, with surgical masks to the left and with FFP2 masks on the right. In these graphical representations, we can see a clear decrease in the efficiency of the system due to the use of masks. After all this, we have been able to find some trends in errors. The classification's errors are consistent with the gender of each speaker. Moreover, there is a frequent error. Speaker 17, when wearing any face mask, is not correctly identified in many cases. The conditions for obtaining the participants' recording do not differ from those of the rest of the participants. It's worth mentioning that this person had a strong accent. Could the accent be the reason for his misclassification? The accent is a characteristic that usually generates problems for speaker recognition system, so this could be the explanation. Therefore, we can say that the first hypothesis is proved. The use of any mask leads errors in the ASR model. However, the second hypothesis does not. The automatic system, when using speech with FFP2 masks, gives clearly better results than when using speech with surgical masks. To find a possible explanation for this, we have extended the study with the analysis of the intensity level of speech.
It was decided to extend the study by applying intensity analysis because during the recording of the audios, it was systematically perceived that the speakers tended to increase the loudness of their voices with FFP2 mask. The acoustic data were measured with Pratt. In the figure, we can see the average intensity so obtained for each sentence in each condition. As might be expected, the audibility of the voice has changed while wearing a mask. The intensity level decreases in the case of surgical mask, and with FFP2 mask, the intensity is higher than in the case where the mouth is less covered or not covered at all. These results are recurrent for all speakers. And it is interesting to note the repeated increase in loudnesses values for all speakers, which leads us to think that this may be the explanation for the non-verification of the second hypothesis. But why this happened? The mask act like a low-pass acoustic filter, and in this unfavorable speech condition, speaker can adapt their phonation to compensate the action of this filter. With the use of the mask, we have the sensation that less audibility is produced, and we increase the speech intensity. Finally, we present the conclusion reached. It has been observed that the system experiences a deterioration of its performance when the set of audios is used with both type of masks. We can see that a lower percentage of accuracy was obtained for the surgical mask audios than for the FFP2 mask audios. This may be because of the filter of the acoustic filter of these masks that produce an alteration of voice perception. Due to the specification to the FFP2 masks, this alteration is even higher, resulting in an increase in the intensity of the voice to counteract this effect. The slight degradation of the results indicates the capability of the state-of-art recognition systems to mitigate the face mask mismatch. In a forensic field, these results underline the importance of obtaining samples under the same conditions to achieve a better identification result. Therefore, although the use of specific softwares to compare voice can be useful, but it should not be the only source of information, and forensic experts' analysis is desirable. To conclude, the following points will be considered as future lines of research: increase the number of speakers and the utterances to test the effect of wearing masks, include more linguistically diverse speakers in the training data, add both noise and words that hinder intelligibility to test the robustness of the model, and finally use deep learning algorithms to perform an automatic acoustic features extraction.
Thank you so much for your attention. Hopefully the topic has caught your attention. Don't hesitate to write to us if you have any questions.
And remember that you can find the full paper in the conference journal published by Springer.
Bye!